So a mutation is a change in the genetic information. This is usually going to happen during DNA replication when there's a mistake that doesn't get caught in the proofreading of the DNA. These can be good, they can be bad, they can be completely inconsequential. However, a mutation can affect a protein, and so that's how it has an effect on an organism. If it changes the DNA, and then that resultingly changes the protein that's made, that's how we end up with a mutation that causes a change in function. So some mutations are called point mutations because they change only one nucleotide. So here we can see a point mutation which causes sickle cell anemia. So here's the wild type beta globin for hemoglobin, which in the template strand is supposed to be CTC. However, it has a point mutation here from CTC to CAC. What ends up happening in the mRNA is instead of getting GAG, we end up with GUG. So you can see how that's going to change the second nucleic acid in this codon. So here's the codon, GUG. Changing the first or the second one here is going to usually cause a change in the amino acid. Sometimes we have some wiggle room in that third codon nucleic acid, and it doesn't always change the amino acid. So the correct amino acid is supposed to be glutamate. However, because of this mutation, because now it's reading GUG, the cell is going to make the protein with valine instead of glutamate. So this point mutation, this change in this one letter from T to A, has caused the wrong amino acid to be put into this protein. And that is going to drastically affect the shape of the blood cell to cause sickle cell disease or sickle cell anemia. These are called substitutions, where one nucleic acid replaces another one. So this is called a nucleotide pair substitution. We had an A, it got replaced with a T. The codon is still the same length, it's still those three. However, one is going to replace the other. And there are three different types of substitutions that are defined based on what happens to the resulting amino acid. So a silent mutation is going to have no effect on the amino acid. So if it was supposed to be threonine, even though there's a change, it's usually going to end up as threonine. This is usually thanks to that redundancy in the genetic code. So this is often going to happen with a mutation in that third section of the codon if it's going to change from one to another one, but it still codes for the same amino acid, then you end up with a silent mutation. A missense mutation is going to still code for an amino acid, just a different one. So this is what we saw with the hemoglobin, where it was supposed to be threonine and instead it got changed to, where it was supposed to be glutamate and instead it got changed to valine. So the resulting protein is going to be the same length. All of the amino acids are going to be correct except for that one. So this one, if that one amino acid changes the shape drastically, like it does for hemoglobin, might cause a really detrimental effect. But if it's going to be changed out with an amino acid of a similar shape, it might not have that big of effect on a protein, just depends on which gets switched out for which. The third type of substitution is called a nonsense mutation. So this is going to change from coding for an amino acid into coding for a stop codon. So instead of coding for glutamate, if we changed it from glutamate to a stop codon, then we would end up with a really short protein. It would be completely non-functional. It would stop there instead of making the rest of the protein, and this is going to be a non-functional protein. So as far as severity, silent mutations have no effect, so these are not going to cause detrimental effects. Missense mutations sometimes cause a detrimental effect, and most nonsense mutations are going to cause a detrimental effect to the protein. So here we can see a mutation. So we were supposed to have a C here, and instead we got a T. So this now says TCG instead of CCG. And so we can see that is, here's my codon. That's going to be the first spot in the codon, so that's probably going to change the amino acid. So what we see in the RNA is we have AGC. We were supposed to have GGC. And originally we were supposed to have glycine, and it ends up changing it to serine. So we had an amino acid, it got changed to another amino acid. This is going to be a missense mutation. Here's another substitution. We were supposed to have a T right here. It got changed to an A. And as a result, the codon changes from AAG to UAG, which is a stop codon. So it was supposed to code for lysine and then continue with phenylalanine and glycine and then a stop codon over here. However, it coded for a stop codon early, and this protein is going to be cut short. So this protein is going to typically be non-functional because it doesn't have all of its amino acids. This is going to be a nonsense mutation. And here we go. We are supposed to have a G right here. Instead, we get an A. This A is going to result in a codon being GGU instead of GGC. Here you can see that that's the third letter of the codon instead of the first or the second. So this is where we have that wobble room where it might code for the same amino acid. And if you go check the codon chart, that GGC and GGU do indeed both code for glycine. So we're going to get the same exact amino acid out of this one or this one. So this is going to be a silent mutation. Sometimes instead of replacing a nucleotide with an additional one, we actually just add in extra ones or we delete them and don't replace them. So an insertion would be adding in an extra nucleotide where there wasn't one before, and a deletion would be removing a nucleotide without replacing it with another one. These typically have disastrous effects on the protein because they change the entire reading frame. So these are called frameshift mutations. So let's think of the codon as a 3-letter word. So the cat ate the rat. When we have a substitution, like we saw previously, where we change one letter with a different letter, we might see some changes and it might not be that big a deal. The cat ate the bat. So this is still an intelligible sentence. We still have 3-letter codons. Now, instead of eating a rat, this is eating a bat. So that might be like having a missense mutation where we changed one word, but we still get a word. A frameshift mutation is not going to make sense. So let's say that we're going to delete the letter E. So let's have a deletion. From the original one. So we get, that's a C. None of these are words, that's the word there, her, and at. So we get something that doesn't make any sense. So if I tried to read that, it'd be like the k, atta, te, her, at. That doesn't make sense. What we've done is we've changed the reading frame. By removing the E that was here, we've shifted all of the letters over by 1. And so now the words are not starting when they're supposed to start. The same thing can happen with an insertion. So this is a deletion. If we have an insertion, we get an extra letter. So what I did is I added an A here. So we get the, eka, tat, eth, era, t. It doesn't make sense. We've shifted the entire reading frame this way. So now all of the codons are wrong. So a deletion or an insertion of a single nucleic acid, of a single nucleotide, can be really disastrous. Sometimes we have an insertion or deletion of an entire codon, and so that's usually less harmful. So let's do an insertion of a whole codon. So the fat cat ate the rat. So when I insert an entire codon, a 3-letter word in here, the reading frame does get shifted over, but it gets shifted by an entire codon. So the codons themselves stay intact. We now have something intelligible. We can read it. The fat cat ate the rat, only we're going to end up having it just be one nucleic acid or one amino acid longer than it would have been. This may cause a problem, it may not, so it's less likely to cause a problem than these two, which are completely nonsense, totally don't work. Here's an example of a nucleotide insertion. So up here we saw that the codons were TTC, and now we have an extra A, so the new codon is going to be ATT. So this is going to change it from coding for lysine to coding for a stop codon. So this is going to have a disastrous effect on this amino acid. Here's a nucleotide deletion. So we had an A up here, and we're going to remove that A and cut it out. So what used to be AAA is now AAC. So instead of coding for phenylalanine, it's going to code for leucine. Instead of coding for glycine, we're going to code for alanine. Instead of coding for a stop codon, this is going to continue on and continue to code for nucleic acids until it either runs out of mRNA or randomly reaches a stop codon somewhere else. However, this is going to completely change the protein. So it was supposed to be 4 nucleotides long. It was supposed to be 4 amino acids long and then stop. But now we're going to have it being 4 amino acids long with the wrong ones, and then it's just going to keep on going. So this is another problem with a frame shift. And then last one here we have is a 3 nucleotide deletion. So this is going to delete an entire codon. So it doesn't change the reading frame, it just makes it shorter by 1. So this codon here that was supposed to be TTC just gets removed. So we're going to basically just remove this lysine and skip from methionine to phenylalanine, and then this protein's going to be 1 shorter. If that 1 shorter causes a really big problem, then that might cause a problem. However, if losing that 1 amino acid doesn't cause a huge problem for the function of the protein, then this may not be a problem for this specific individual. Mutations can occur whenever we have errors in DNA replication, recombination, or DNA repair. There are external elements called mutagens that are either chemical or physical elements that can cause mutations. These vary into a variety of different categories. A lot of the different mutagens that we have cause cancer, so they're also called carcinogens because the mutations they cause are carcinogenic, where they are going to increase the likelihood of getting cancer. So some common mutagens, UV radiation, which is going to lead to thymine dimers, possible exposure for skin cancer. X-ray radiation can cause cancer, so many of the early studies of X-ray radiation caused early death in those scientists. We know that wearing a lead-lined vest can help prevent the X-rays from entering. Tobacco products, smoking, we know that those cause lung cancer. There's a lot of other chemicals, formaldehyde, things like that, nitrates that are found in red meat and processed meat, like things like hot dogs, bacon, sausages. Those have been linked to colon cancer as well.